Now, let's talk about what a generator coroutine is. Here's where the terminology starts to get very dicey. I said that the core Python interpreter names everything a little bit differently than how we typically refer to these things. And it turns out that the Python standard library also starts to get a little bit weird about how it names things around Python 3.6, where before Python 3.6, what we used to call coroutines was one thing, and then after Python 3.6, what we call coroutines is another thing. So here I'll make that uppercase, lowercase distinction, and I'll talk about actually I won't talk about a capital C collections.abc.coroutine, which is definitely not what one of these things is. In fact, if we ask, in fact, you can see this is where it starts getting really dicey. If we ask Python, is this thing a generator? It'll say, no, it's not a generator, because it'll say this thing is actually a function. And if we invoke this thing to get the generator instance, it will say this thing is a generator, but we're going to call this a lowercase c coroutine, not an uppercase c coroutine, because Python doesn't consider this to be an uppercase coroutine. I know the terminology is very confusing, and so here's what we're going to do. Anytime we talk about something that looks like a generator but has this coroutine-like behavior, where historically we would have called that a coroutine, maybe with the lowercase c, we're just going to call it a generator coroutine. It's a very clumsy term, but it's the best that we have available. Let's talk about what it is. Well, let's say we have a non-concrete, non-materialized iterable. We have, say, a representation of an infinite sequence of values, like something that loops. So we have something where it takes a value and it runs forever, just looping over that value. So here we have some generator instance looping over the value 1, 2, 3. And if we look at this, we'll see that's just our generator instance. If we call next on this, we'll just get 1, 2, 3 forever. If we put this into a for loop, this for loop will never terminate unless we explicitly break, because this is non-finite. Well, what if it's the case that as a consequence of how we might be using this looper, we want to change what it iterates over? Think about this. We create an instance of this looping. Then we send that instance maybe to some class somewhere, maybe a data class with some, data. Here, we'll do something like this, and we don't actually care what that actually happens to be. Well, if we do that, and so here we'll pass this into our T, this will be our object. And then maybe there's methods here on this, like some function method here, and this does return next self.data, something like that. And maybe in its post init, it does something like this, self.data equals iter self.data, which remember is a safe thing to do, because if the thing's already an iterator, you just get that same iterator back. Well, if our interaction with this object is really only through these methods, it may be the case that we kind of want to swap out what data we're working on, and we may not be able to do object.data equals ... This may be hidden by some convention. For example, we might say this is a private piece of data and you're not really supposed to touch it, so we can't really change what this thing loops over. However, generators are fundamentally immutable entities, and generators support more mechanisms than just advancing to the next step. The other mechanism that a generator supports is, well, you can throw an exception if you want. That doesn't seem to be that useful for our case. So here we could throw a type error. We can throw exceptions up into them. Okay, that's not that useful. We can close them. We can say, no more work needs to be done. You're done. And that's not that useful. Or we can send information into them. So we could send into this thing 456. Now we can't yet send into this thing at 456 because we get a can't send an unknown value to a just started generator error. But if we do at least one next first, we can send a value in. Now let's take a look at what the outputs are. Obviously, this next here is going to be the output 1, 2, 3. And this send here, well, it's going to be the output 1, 2, 3. It turns out that that send is really just equivalent to, or sorry, that next operation is really just the same thing as vi.send with a none value. And it turns out that this generator is bidirectional. It can send back to you parts of the computation, and it can also take in some input. It's actually a bidirectional. It's like a function that just lingers in the background with some state. Well, since that next command is basically the same thing as sending none, what we can do is we can say if this new value is not none, then we'll set the value to whatever the new value is. Otherwise, we'll just keep going. And of course, we have to parenthesize this just a little bit deeper to satisfy the parser, but there we go. And now you can see we have a little looper where we can latch in a new value. And if this were then composed with some other object, you could see where, as long as we can expose that underlying entity, we can actually mutate what it's working on. Here you can see the bidirectional behavior of it. Now, this can't send a non-none value to a just started generator problem tends to be clumsy enough in practice that when we're dealing with these generator coroutines, we may often choose to avoid the problem entirely by doing something that we call pumping. What that means is we'll say that when we have a Python function, it's often the case that the Python function will have both data and modal parameters. That is to say, the function will have some data that it operates, as well as some mode that it operates on that data. For example, if you're doing a pandas.read CSV, the data you're operating on is the CSV file. The mode that you're using is maybe if it's a CSV versus a pipe separated file or a tab separated file, they're flags or options or other things that control how you go about doing the operation. If we have a generator, well, it's very likely that it may have data and some modes as well. Note that you can see that single star there. It's very, very likely to be the case that the modal parameters of a function or the modal parameters of a generator are indicated as keyword-only arguments. Why? Well, the data that a function operates on is usually pretty obvious. Read CSV, what does it operate on? A CSV file. But the modal parameters might be pick and choose. Well, read CSV sep equals, maybe not everybody cares about changing the separator. Read CSV has a delim option. Do you know the difference between delim and sep? Is there a difference? Whatever the case may be, it may be necessary for us to make those keyword-only arguments in order to make this a little bit more readable, because not everybody is going to be aware of all of the different possible modalities. Well, it turns out that if we have a coroutine, which mechanically is really not distinguishable from a generator, it's just a generator where you send information into it and you use that yield not as a statement, but as an expression, you get a resulting value. Well, it turns out that if we look at this structure, we can send data into this coroutine in two different ways. We can send the data in either by calling it with some arguments, or we can send data in via that yield, via the .send on using that yield as an expression. And you might have a question, well, do I send the data in when I first construct this thing, or do I send the data in each step along the way? Well, anytime there's a decision that needs to be made, I always try and find what is the answer that allows me to avoid having to make the decision, which makes this very clear and unambiguous. And the answer here is when we deal with coroutines, we may choose to have the coroutine only set up its modalities and then only take data via that .send. So if we were to go to this looper and we were to think about how we might do that, what's a modality for the looping? Well, a modality for the looping might be something that we do to the value we loop over. It might be something like an operation that we perform. So we might say here, by default, this performs some operation on the value. Maybe it's some operation that is performed on the value each step along the way. So maybe I'll do value equals operation of value. So maybe I can have like a looper, but also like an automatic decrementer. Maybe we'll say by default, this is a lambda that takes x and just decrements it by 1. And the data that it's operating on is the value that it's going to work with. And so we'll put a yield at the beginning here, and we'll take in our first piece of data like this, which means if we want to use this thing, we'll start it with maybe the default operation. We'll have to do a dummy next here, because that yield doesn't yield anything useful. This is just yielding some non-value, a none value, essentially. And then we'll send in 1, 2, 3. And along the way, we can see that if we start asking for the next piece of this, we'll get at 1, 2, 3, but each step along the way, it gets decremented. And if we want to set this thing back up with like a 4, 5, 6, There we go. Now there's a question as to whether that we should allow that decrementation to happen the very first time or not. We can make this an else, so then, we get that original value, we get the 456. Those are small details of our implementation. Fundamentally, however, you can see that this here is kind of ugly, and the difference between that next and that send might be a little bit ugly. So what we could do is use a decorator in order to normalize this and in order to avoid having to do this dummy next. What we'll do is we'll set up a decorator that takes the coroutine, and what it's going to do is it's going to create an instance, or it's going to create a brand new function. That brand new function takes some extra arguments. We don't really know what they do. It's going to instantiate that coroutine with those arguments, and it's going to take that result, that coroutine instance, and it's going to do the dummy next for us. And then what it's going to do is it's going to say, you know what, I don't like the next versus send dichotomy that much. I feel like it looks a little bit ugly in my code. So what I'll do is I'll do something like this. Create a lambda, takes a value, and I'll return that lambda. I'll combine these pieces together, and now I have the exact same thing that I had before, but with a little bit cleaner of an API. In fact, what we end up with is something that looks very, very much like a function. Here, you can see it's a function where if we call it with some argument, it sets up that argument, and if we call it with no argument, it just kind of gives us the next value. Now, we can choose exactly the API we want. We don't necessarily have to hide that there's a send method there. We could, of course, just return the ci.send, or we could return, of course, the generator instance here, and we could then always do a .send operation. It really is up to our preference. But one interesting thing you can see here is a generator coroutine is also kind of like a function that has some lingering state, some lingering memory. Well, that's kind of useful. Now, I very briefly want to talk about something that we are not actually going to cover: asynchronous tasks and asynchronous coroutines. In Python 3.6, we gained new keywords for representing what oftentimes people used to call coroutines, but not quite when they were referring to the use case that I showed you with the generator coroutine. It starts getting a little bit complicated terminology-wise. But they created asynchronous functions or asynchronous. I like to call these things asynchronous tasks. The documentation likes to call these asynchronous functions. And the collections module, well, it calls this thing the capital C coroutine. So for our purposes, let's just talk about generator coroutines, the thing we just saw, as well as asynchronous tasks, and avoid the capital C coroutine terminology entirely, just because I feel like it gets very confusing for really no benefit. But we can see if we instantiate this thing, we need an is instance, gives us a coroutine. It complains to us that the thing was never awaited. That's no big deal. Just pay attention to this last line here. Well, this represents some operation that was broken down into parts. Well, that's the same thing as a generator, but where there is an event loop that is supported by the language itself, by the async.io module, that takes those parts and decides how to schedule those parts. And so, for example, if I extend this example very slightly, I'll pull in from async.io, run and sleep. I'll have this thing run forever, have these things sleep for a second in between each pass. Maybe I'll start it with a number and I'll print out the number. Well, I should be able to comment that out, show you a very simple example of how this all works. We'll gather two tasks, one printing out 1, 2, 3, one printing out 4, 5, 6. Remember, these are just basically functions that are broken down into parts where behind the scenes, that event loop is triggering which part it wants to run when. And so this gives us the ability to interleave this behavior. That's why you can see this terminology coroutine was used, very similar to what we looked at before, but with post Python 3.6, different, its own specialized syntax and its own specialized. It turns out that it is possible to also write an asynchronous generator coroutine, like a lowercase c coroutine, uppercase coroutine. It will look something like this. I would call this myself an asynchronous generator coroutine. I don't know if there's a good name for this thing, but you can actually do something like this if you want. We'll take the example from above, and this is going to get a little bit wild, and we'll make this thing yield the number. So now this is an asynchronous generator. And this is actually be an asynchronous coroutine if we want. And then to actually make this work, we will have to do the following. Here we'll say async for each number in this thing, and we'll do something like this and tap this number. It'll be the simplest example we can show of this, and it gives us the same general output, but you can see here we have something with this yield statement. Again, we won't cover this in much depth, although when we look at the APIs that we might use for writing bots, it may very well be the case that we're going to apply everything that we see when we talk about regular generator coroutines, except implicitly as a consequence of those frameworks being async IO, we basically implement them with slightly different vocabulary, with slightly different mechanisms, but the core ideas are the same.